Folks, today I'm going to show you one equation, this equation, the FLRW metric. This equation describes the entire universe. This is the equation of our universe. Let's go ahead and derive it from the Einstein field equation. Folks, welcome to the next episode of General Relativity. I'm your host, Rev Bari, Brown University physics grad student, and today I'm going to show you the FLRW metric, one equation that describes our entire universe. Let's check it out. So here's my flat sheet of paper, and here's a right triangle with side lengths of dy, dx, and let's call this ds. Okay? Now, I know from Pythagorean theorem that ds squared is dx squared plus dy squared. Okay, great. Now, this is if I have a flat space and time. I can generalize this equation by saying that ds squared is gij dxi dxj, where gij is some metric given by 1, 1 and 0, 0. It's just the identity. So what do I mean by why are these two equations the same thing, you might ask? Well, I can show you that directly here. When I write gij, dxi, dxj, what I'm really writing is a sum over all the possible values of I from 1 to 2 and all the possible values of j from 1 to 2 of gij, dxi, dxj. And so what is this? This is g1, 1, dx to the 1, dx to the 1, plus g1, 2, dx to the 1, dx to the 2, plus g2, 1, dx to the 2, dx to the 1, plus g2, 2, dx to the 2, dx to the 2. Now notice that because this metric is only diagonal, the off-diagonal components are simply 0. So what does that mean? That means that all of these terms are 0. So this is the first row, second column, so G12 term and the G21 term, these guys are both equal to 0, right? And so that means we're just left with these two terms. And so what are these two terms? G11 is simply 1, so I have 1. And then what is dx1? Well, remember, x is some vector that's composed of the following, x1 and x2, where x1 is x, x2 is y. So g11 is x times dx1, which is dx, dx1, which is dx, plus g22 is also 1, times dx2 is dy, and dx2 is also dy. And so you can see that ds squared is really just dx squared plus dy squared. And so you can see that these two are just two sides of the same coin. A rose is still a rose by any other name. So let's erase all of this, and now let's proceed to the second upgrade. So we've seen how to express a flat space-time in these coordinates. Now, how do you express a sphere? Okay, how do we represent a sphere using this kind of a language? Well, for a sphere, what I'm going to do is as follows. So this over here, I'm going to call this dx, dx with a bar squared. And instead of s, let me just call this L for length. So a small length is just dx squared plus dy squared, or dx with a vector arrow on top squared. Okay? So now the question becomes, okay, how do we represent a sphere in this language? So the way we represent a sphere is as follows. A small step on the sphere's surface is dx squared, what we had before, plus du squared, where u is some new parameter that allows us to express this 3D sphere in a 4D space. And then we have the condition that this sphere has a constant curvature. It has a constant radius. Let's call it r0. So that means x squared plus u squared must equal r0 squared. That's if you have a sphere. Now we upgrade to the last possible geometry, which is as follows. This right here is a hyperbola, or it might be a hyperbola if I drew it correctly. A hyperbola is like a Lay's chip. And so we can express this with the following equation. dl squared is equal to dx squared minus du squared. That minus sign contains all the information about the fact that this is a hyperbola, not a sphere. The minus sign makes all the difference. And so now we're going to have r naught squared is x squared minus u squared. Okay? Great. So now we've got three different ways to express three different geometries. A flat geometry, a positively curved geometry, and a negatively curved geometry, like a hyperbola. Actually, I should put a minus sign here. Okay, great. So now what I'm going to do is combine all of these three geometries into a single geometry. So I'm going to first combine my lengths dl squared as follows. So I can write that in general, for any three of these geometries, I can say that dl squared is equal to dx squared plus minus du squared. That's what we've got by combining these three dl's in general. And then let's combine our embedding conditions so that we find that plus minus r naught squared is equal to x squared plus minus u squared. Okay, good. Now, what we're going to do is use these two to express dl squared only in terms of x and r naught, not in terms of u. So here's what I'm going to do. I'm going to take my embedding condition and take the derivative of both sides. So the left-hand side is going to become a constant 0. The right-hand side is going to become 2x bar plus minus, 2x hat or whatever, 2x vector, dx plus minus 2u du. Okay, I cancel out the 2's, and so I'm left with what? If I just solve for this, then I'm going to get minus x dx is equal to u du, right? And now remember, there's a plus minus in front of the u du. Move that to the other side, that gives you minus plus, because you had a minus in front of the x. So now we have that u du is equal to x dx, or minus plus minus x dx, right? Now, can we take out this u? Can we take out this u? Let's see. I've got this condition on u. So maybe if I solve for u here, we can get something. Let's see, where's my u? Okay, let's solve for u here. So I'm going to have minus x squared plus minus r naught squared is equal to, let's see, I've brought this over to the left side. I've got plus minus u squared. Okay. Now, what I'm going to do is take this to the other side. So the plus minus is now going to become, once again, it's going to become a minus plus x squared plus minus r naught squared is equal to u squared. Okay, great. Now, based on this, how can I exploit this over here? Well, I can square both sides, can't I? I can square both sides. So I have x squared dx squared is equal to u squared du squared. Now notice that this is a vector on the left side. This is a scalar on the right side. How do I make a scalar out of this? Well, I'm going to erase my squares, put a dot product here, and now I'm going to square it. Okay, so good. Now, for u squared, I've got this simple expression that I can plug in. So if I just come over here, let's bring it over here. I don't know why I've been stooped so low. So I've got, where are we? So I've got x dot dx squared. So let's be straight. Let's be clear about this. So u squared du squared is equal to x dx squared, okay? And then we also have the condition that u squared itself is minus plus x squared plus minus r naught squared, okay? So now I can solve for du squared here and find that du squared is x dot dx squared divided by u squared, which is this, and that is simply minus plus x bar squared plus minus r naught squared. Okay, so now let's see. I've got du squared, and I know that dl squared is simply dx squared plus minus du squared. So let's bring this over here. So this tells me that dl squared is equal to dx squared, and then I've got plus minus this stuff here, x dot dx squared divided by x squared plus minus r naught squared. And so now we've almost arrived at the equation for the universe, but not quite. Now we're going to transition into spherical coordinates to make this easier to describe. So that's going to be as follows. First, I'm going to say that x is given by the coordinates r theta phi, so that dx is given by the coordinates dr, d theta, d phi, and actually let me erase this here. And finally, now that I've got these two, I can take the dot product of x dx, and that gives me simply r dr, neglecting the angular coordinates. And what about x magnitude squared? Well, that's simply going to be r squared, right? Okay, great. And yeah, that's pretty much it. And do we have to do dx squared? Sure, let's do dx squared. So if I do dx squared, that's going to be r squared sine squared theta. Hopefully you can see up to that point. R squared sine squared theta d theta wait 1 second, what is it? R squared, let me try to remind myself. It's r squared sine squared theta d theta squared plus d phi squared. Something like that. Don't hold me at gunpoint about the actual integral measure, but that's the idea. And anyway, I'm going to replace this by the angular symbol omega. So now we can come over here and we can replace everything as follows. So dl squared is equal to dx squared, which is simply this. What is that? So that's r squared. And actually, I should also have a plus dr squared here. So I've got r squared, dr squared, plus r squared, d sigma squared for the angular integral measure, and then plus minus, we've got this term, x dot dx is simply r dr, and if I square that, that's r squared dr squared, divided by, now x squared is given by r squared, so I have r squared plus minus r naught squared. Okay, so this is the idea. It's starting to take form. We're almost there, but let's not rush it. The next thing I'm going to do is introduce the curvature scalar k. The curvature scalar k is going to tell you what kind of a surface you have, and it's going to be given by the number k. K is going to be 0 if you're on a flat surface. It's going to be positive 1 if you're on a curved surface that's positively curved like a sphere, and it's going to be negative 1 if you're on a negatively curved surface like a hyperbola. So this is a flat Minkowski spacetime if k is 0. This is a sphere if k is 1, and this is a hyperbola if k is minus 1. Okay, good. Now, if I look over here, where can I introduce k? I can introduce k in two places. First of all, this plus minus can simply be replaced with a plus k, and this plus minus can be replaced with a minus k. Okay, so no pun intended. So now I'm going to come over here. Hopefully you'll still be able to see what I write. So dl squared, a tiny step in my toy universe, is going to equal r squared dr squared plus r squared d sigma squared, okay, and then plus k r squared dr squared divided by r squared minus k r naught squared. Now notice I've got something a bit crazy here. Oh, by the way, I think my plus minus should be with this r squared, not with the other one. So this should actually be kr squared minus r naught squared. Okay. So now we're almost there. Now what we have to do is do some fishing around with the signs here. So let's take a look. Let me erase some of the previous equations here, and let's try to extract our equation from here. So we have dl squared is equal to r squared dr squared plus r squared d sigma squared, and then plus kr squared dr squared divided by, let me put the r naught squared in front. I know what I'm doing is technically illegal. Don't shoot me in the face. Oh, wait, you can't because you're on the other side of the screen. So what I'm going to do is divide both the top and the bottom by 1 over kr squared. And so let's see. That's going to give me, maybe I'll stick with kr squared minus r naught squared. Okay, so if I divide top and bottom by kr squared, then I get dr squared, and then 1 minus r naught squared over kr squared. Okay, good. And then plus r squared dr squared plus r squared d sigma squared. Okay, almost done. Now let's see if there's anything else we have to do. Now instead of r squared, let's put common denominators here. So, or actually, ooh, right. Let's play this out. So let's play it out the long way. So this is going to be r squared dr squared. This should just be dr squared, actually. I just realized, because the integral measure just is going to be dr squared. This is not going to be contained in the brackets here. So this will just be dr squared. This will just be dr squared. And so now if I multiply this by kr squared minus r naught squared to have equal numerator and denominator, then I have this, okay, plus r squared d sigma squared plus kr squared dr squared. Okay, kr squared minus. Okay, so let's see. I'm getting some funny results because I should have a minus sign somewhere, and my minus sign, somewhere I'm missing a minus sign essentially. But if I carry this through, then I should get, let's see, I'll get r naught squared dr squared over something like r naught squared minus kr squared, and then plus r squared d sigma squared. Okay, so if I solve all of this through and I do all the algebra, then I'll find that dl squared is equal to dr squared divided by 1 minus k r squared over r naught squared. Okay, something like this, and plus r squared d sigma squared. And so now, finally, to wrap it all up, that means that my metric, my final metric for the whole universe is going to be ds squared, which is a space-time step not only in space but also in time, which is equal to dl squared, which is equal to minus c squared dt squared plus some scale factor a squared of t times dl squared. So that means the metric for our entire universe that describes the expansion of our universe is minus c squared dt squared plus a squared of t times dl squared, which is given by dr squared divided by 1 minus kr squared over r naught squared plus r squared d sigma squared. And so this, ladies and gentlemen, is the metric for our entire universe. This is called the FLRW metric, Friedman, Lemaitre, Robertson, Walker metric. And so this metric tells us how our universe expands. In the next episodes, I'll be analyzing this metric step by step. But note that you can already gain some intuition for what kind of a universe we have and play around with toy universes, which is a crazy thing to say, by checking what happens if the curvature scalar k is +1, which represents a spherical universe, if k is 0, which represents a flat universe. Spoiler alert, that's what we might be heading for. And if k is -1, which is what happens if we have a negatively curved universe like a hyperbola. And right now I'm debating whether it's r squared over r naught squared or r naught squared over r squared, but you can easily check by doing the following. If r squared is very huge, then what happens is this denominator gets very negative, and so that doesn't really make much sense. On the other hand, if you had r naught squared over r squared, then when r gets very big, this would converge to 0, and so you'd just be left with dr squared. So that means at very far away regions, it just looks like flat space-time. Another way you can test this out is that if r was in the denominator, if r was in the denominator, then r equals 0, the origin, would be causing problems, right? So you know that that can't be true. Whereas if r is equal to 0 here, we simply have dr squared, so no problem. So okay, folks, this is the Friedman, Lemaitre, Robertson, Walker metric, the FLRW metric. This is the equation that describes the whole universe. Thanks for watching.